Hello, Math 1365, Mathematical Reasoning. This is sample test 3. Sample test 3 covers relations and functions, which is modules 7 and 8. So let's get started with number 1. We consider the relation R on the integers where xy is an R provided x is the absolute value of y. And we have two parts here. The first one, we want to explain why R is not a function from z to z. So let's talk about what does it mean to be a function. That can help us answer why R is not. So first of all, a function is a relation fundamentally, and that is okay. We're given a relation. But then there's more. It needs to be, well, this first set, which if it was a function, we would call that our domain. It needs to be the case that each element in here appears as the first coordinate in exactly one ordered pair in the relation. This is where things will go wrong. So let's just say consider 2, which is certainly an element of z, as 2 is the absolute value of -2, and 2 is the absolute value of 2, we see that 2 and 2 minus 2, these are both elements in R. And this is the issue, right? We have element 2 in z is the first coordinate in 2 elements of our relation. I'll just say thus, R is not a function from z to z. So this is one justification. You could certainly come up with others, but this is wonderful. Letter B, we want to circle all elements which are in our inverse. This is the inverse relation. So first of all, what is our inverse? Well, maybe I'll write it up here just for this relation. Our inverse, well, you interchange the first and second coordinates. This is the inverse relation. So this would be yx such that x equals the absolute value of y. Okay. Well, now let's go through one by one and see if this is the case. On this first one, is this the form yx such that x equals absolute value of y? Yeah, 1 is the absolute value of -1. So this one is in our inverse. Now, what about this one? Is this of the form yx such that x is the absolute value of y? No, because -1 is negative. It's not the absolute value of anything. This one's okay. And then the last one is definitely not the case. Would this be yx such that x is the absolute value of y? Once again, no, because -1 is not an absolute value. And so here are our two answers here. Now we move on to number 2. Capital R is the relation defined on real numbers where for real numbers x and y, x relates to y if and only if x minus y is an integer. So we need to prove R is an equivalence relation. We have 3 things to prove. We have reflexive, we have symmetric, and we have transitive. So first for reflexive, we need to let's say A be an element of R. And then we need to show that A relates to A. And let me do this. Then it's clear. I mean, real numbers. Well, notice A minus A is 0, and 0 is certainly an integer. And so we get that A relates to A. I want to prove this relation is symmetric. This is what I will do next. So we suppose we have 2 real numbers, A and B, that are related. So we suppose A and B are real numbers and A relates to B. We want to show that B relates to A But what do I know? Well, I know there exists some integer with a minus b equals this integer. And then to get that b relates to a, I need b minus a equals an integer, but I have this. I just need to write it down. We see that b minus a equals negative n, and minus n is an integer because n is. So what do we get from this? We get that b relates to a, and this proves symmetric. Now we are moving on to transitive. This is the last property that we need to finish the proof in number 2. This time, I need to start off with 3 real numbers. So we suppose A, B, C are real numbers with, well, we had A relates to B and B relates to C. I need to prove that A relates to C. This is what it means to be transitive. So we are assuming both of these though. So now I have 2 integers. There exists maybe n, m, and z with, well, we would have a minus b is n, and we would have b minus c is m. Well, what we want to say something about is a minus c, but you notice that a minus c is equal to a minus b plus b minus c. And this is n plus m. And then as n plus m is an integer, a relates to c. And this is the proof. We have proved this relation is reflexive, symmetric, and transitive. And therefore, we have proved we have an equivalence relation. Here is my box ending the proof. And this is the end of number 2. Number 3, this is also a question involving an equivalence relation, but we are not asked to prove that this is an equivalence relation. We're asked to do something a little bit different. So let's read the problem. We start with the integers between 1 and 9. That's our set A. And then we define a relation on A by, for x, y, and a, x relates to y if and only if x equals y or x plus y equals 10. And then we're told, well, for example, 3 relates to 3, and also 3 relates to 7. So what we want to do is find the distinct. Distinct is an important word. We only want to list each equivalence class one time, and then we'll also list all the elements of each equivalence class. So we have to go back and remember what an equivalence class is, for instance. So how do we start something like this? Well, you pick one element in A to begin with. I will pick the first one. And so I'm going to find the class of 1. This is not ordered pairs. Equivalence classes contain elements of A. In fact, one thing that we discussed is that the classes partition A into disjoint sets. So the class of 1, what this is all x in A such that x relates to 1. That's what this class is, but I need to list all of the elements. So first of all, certainly 1 relates to 1. 1 is in its own equivalence class, definitely. But then also there's this other part, x plus y equals 10. So 9 is also in this class, but that's about it. That's all for this equivalence class. Now move on. We would not, for example, next write the class of 9 because it's already on the paper or my iPad. The class of 9 is the class of 1. If I listed that, I would not have distinct classes anymore. There would be a duplicate. So we just pick some element in A that's not listed so far in the classes we've written down. For example, 2 has not been listed so far, and we will write down the class of 2. Well, definitely it contains element 2, but then also what element, when you add it to 2, gives you 10? This would be 8. And this is all for this class. And then we move on. We continue this. Let's figure out the class of 3. Well, it contains 3 and also 7. In fact, these are the 2 here. But nothing else. Okay, nothing else. In fact, all of the elements that relate to 7 are in this class. 7 is related to 7. And then the only other element that satisfies either x equals y or x plus y equals 10 is this one. Okay, so now we move on. I need the next one. I pick an element. I would not pick 1, 9, 2, 8, 3, or 7. I already have their classes written down. So pick some other element of A. I can pick 4, for example. We will find the class of 4. Contains 4 without a doubt. Then we need the element such that when you add it to 4, you get 10. And this is element 6. Now, you ask yourself, are you finished? Not yet, because we do not have every element of A in some class. This is how we know to keep going, that we have more classes here. So what's not listed, that's an element of A. That would be element 5. And under this relation, certainly 5 is in this class, but then what element, when you add to 5, gives you 10? That's just 5. So this is the only thing in this class. And now I claim that I'm finished writing down distinct equivalence classes because 1, 2, 3, 4, 5, 6, 7, 8, 9, I have all of the elements of A here. Okay, so I have all of my distinct classes. And just like I was saying, you notice they're all disjoint, and the union of the classes is all of A. This is what happens with equivalence classes. Wonderful. Now we move on. We move on to some problems about functions. The first one, we are defining f from n cross z to z, where f of n m is n plus m. We want to prove that this function is onto, and then we will also show that it is not 1, 2, 1. So this is a great exercise because we have to practice how do you show something's onto and how do you justify something is not 1, 2, 1, for example. So onto. Well, we start over here. What onto says is that every element over here in the codomain is f of something, or it says that the codomain and the image are equal. But the way we organize a proof about a function being onto, you let, say, y be here in the codomain. And then I need to find something over here that maps to y. So I need to find, I'll say an AB in n cross z with f of AB equals y. This is my goal here. So let's just think about this function. We cannot do 0 y. That won't work because this is not a natural number. Natural numbers start with 1 and then 2, 3, 4, 5, etc. Okay, so this wouldn't work, but that thought process can tell me what will work. So let's consider the element, which is 1, and then I need a number such that when I add it to 1, I get y. Well, that would be y minus 1. Certainly, 1 is a natural number, and y is an integer, so y minus 1 is an integer. This is definitely an n cross z, and f of this element, 1 y minus 1, equals 1 plus y minus 1, which is y. And so you notice we have shown f is onto. Fantastic. Now prove that f is not 1, 2, 1. So what we need to do, if we think, of course, this is not finite sets, these are infinite sets, but the idea of not 1 to 1, we have to find 2 elements in the domain that map to the same element in the codomain. That would be not 1, 2, 1. Okay, so let's do that now. Let's see. For example, we can find two elements that map to 0 that are different. So that is going to be my strategy. So let's consider 2 minus 2 and 3 minus 3. These are n cross z. Okay. We have, if you evaluate f of 2 minus 2, this would be 2 plus minus 2, which is 0. And f of 3 minus 3 is 3 plus minus 3, which is 0. So we do have f of 2 minus 2 equals f of 3 minus 3, and these ordered pairs are definitely not equal. So this justifies that f is not 1, 2, 1. This is the end of number 4. Number 5, here we have another function, and this one goes from real numbers to r cross r. And we want to calculate this function at two different real numbers and then prove this function is 1, 2, 1. So we want f of minus 3, and then we want f of 1/2. F of minus 3, well, this would be, maybe I will do a little bit of side work over here. F of minus 3, this is minus 3 divided by 3, and then 4 times minus 3 plus 2, which is negative 1, and negative 12 plus 2, negative 10. So we put that here, minus 1, comma, minus 10. F of 1/2. 1/2 divided by 3 is 1/6. And then 4 times 1/2 is 2. So we would have 2 plus 2. So this one is 1/6 and 4. Okay. This is just evaluating my function. Letter B, we want to prove that f is 1, 2, 1. So in the last example, number 4, we proved a function was onto, and practice how we do that. And then we also justified why a function was not 1, 2, 1. This one, we want to prove a function is 1, 2, 1. Just as a comment, we could also prove it's not onto, but this wasn't asked in this problem. So how do you prove a function is 1, 2, 1? You want to let, say, x, y in your domain, which is R. This is our domain, with f of x equals f of y. This is how your proof should start. To prove a function is 1, 2, 1. This should be your first sentence, except put in whatever your domain is. Let x, y, and r with f of x equals f of y. And then we want to show, in fact, that x equals y. This is how we structure a proof of a function being 1, 2, 1. Well, we have to unravel what this means. We have f of x equals f of y means x over 3, 4x plus 2 equals y over 3, 4y plus 2. If this element in r cross r equals this element in r cross r, the only way that's possible is if the first coordinates are equal and the second coordinates are equal. So I'll just say like this, it follows that x over 3 equals y over 3, multiplying by 3, which is certainly something I can do. We see x equals y. And so this would be the end. That is what I wanted to show. And this is the end of our proof for F being 1, 2, 1. Number 6, this is the last problem on this sample test. We have two functions. First of all, we have the set A, we have the set B, and then F maps A to B, and G maps B to A, and the functions are given. Okay, we are given the functions as ordered pairs. And then we want to calculate G compose F and then answer some questions about it. So it's important to understand that G compose F, this is happening first. F is happening first. And in particular, well, I can go ahead and answer some things about in B, the domain of G compose F is always the same as the domain of F. So I can write that down. The domain would be A, which is the set 0, 5, 8, and 9, without a doubt. But thinking about that, we know how to get started. So I need 4 ordered pairs here. The ordered pair with 0 as the first coordinate, the ordered pair with 5 as the first coordinate, the ordered pair with 8 as the first coordinate, and similarly with 9 as the first coordinate. Okay, and how do we get that? Well, it's composition. In F, 0 maps to 2, and then in G, 2 maps to 5. Okay, so altogether in the composition, 0 maps to 5. And then in F, 5 maps to 3, and in G, 3 maps to 8. So in the composition, 5 maps to 8. In F, 8 maps to 2, and then here, 2 maps to 5. And so in the composition, 8 maps to 5. Finally, in F, 9 maps to 3, and here 3 maps to 8. And so in the composition, 9 maps to 8. Okay, so this is G compose F. Now here, we needed the ordered pairs to figure out the image. The image is the collection here of second coordinates. And you notice I only have 2. All I have is 5 and 8. It is not the case that the image is all of A. Definitely not. A has 4 elements. It's also the case that the image is not the same as the image of G. You see, the image of G is 5, 8, and 9, and the image of G compose F is just 5 and 8. So that's why it was important we wrote out the ordered pairs. Then we can write down the correct image. Letter C, true or false, G compose F is 1, 2, 1. I'm going to say this is false. I will put some justification, even though it says part C, true, false, no explanation is needed, just so that everyone is clear. One thing to notice is that G compose F of 0 is 5, and G compose F of 8 is 5. But 0 is not equal to 8, okay? So that is one way to think about part C being false. You could come up with another example, but this is perfectly fine for justification. So this is the end of sample test 3. Good luck on the actual test. Thank you all so much.